All right. We have started recording. So, uh, so if you both are ready, I think we can start from our end for today's flight safety review session. Is it good?
Yes, go ahead.
All right, sure. So, very good evening to everyone who's present here today and to the two flight safety reviewers for Hebat 2 from Team Malaysia. My name is Vanmita and I'm the project manager for this team called Wow Rocketry SM and also for the project Hebat 2. Our team ID is 113 and Universiti Sains Malaysia. So before we proceed further, let me walk you through what our presentation today would look like. So first of all, we'll start with the technical mission and followed by the team introduction and followed by the subsystem explanations. And lastly, it would be the assembly checklist brief description. So first, our technical mission for this project, Hebat 2. Hebat 2 is our rocket name. So the first mission is to actually achieve the targeted apogee. So in this case, the targeted apogee is 10,651 feet. Followed by, we have a payload mission where it measures the initial values of the rocket during the launch and compare with the theoretical values to validate the reliability of the manufactured COTS motor. It's part of our research for our propulsion project. And followed by for avionics mission, we are developing our own Astrat altimeters. So in that case, it will be storing and transmitting telemetry data to a mobile phone based ground station. And lastly, as part of our payload, it will be recording the flight footage of the rocket. So this rocket specialty is we have improved design for our rocket structure compared to last year, where in terms of manufacturing, last year we purchased the nose cone and the couplers off the shelf, but this year this rocket was fully fabricated by us from the nose cone up to the bottom of the booster pipe. And next we have improvised the fins design. Last year we used fixed design, and this year we have come up with a design where the fins can be removable and detachable. Next, we have an onboard Astrat altimeter for live transmission of the telemetry data, followed by the onboard camera. So this is the rocket overview. And if we see from at the front, the nose cone will carry the payload, followed by the camera. And then in the forward, this part, we have the main parachute. And in between 4.2 and half, we have this avionics bay in the coupler. And at the half tube, we have drogue parachute, followed by the booster airframe section is dedicated for the motor. And lastly, we have this detachable fins. So this is our rocket design overview. Next, this is the executive team who will be focusing on the team management, finance aspect, and also the safety aspects. Myself, Vanmita, as a project manager. We have Fatin Shuhada as safety officer and Viveka as finance director. Next, the advisors. We have two advisors who are specialized in computational fluid dynamics and also space mission design and analysis, where they both will be guiding us in terms of payload mission and also analysis aspect of the projects. And we have mentor Julian as our flyer of record and mentor as well. His educational background is Bachelor of Aerospace Engineering, graduated from Wichita State University. And in terms of experience, he was the vice president for Wichita State Rocketry Club. And in terms of rocketry experience, he has plenty of experience with a few successful flights. So next, I would like to pass to the Farhana Amsan, who is the structure lead, to present the structural subsystem.
Hi, my name is Farhana. I'm the structure lead for Rocketry. I'll be presenting about the design and methodology that we use for building our rockets, and also the tests and analysis that we conducted for building this rocket. Next slide. All right, this is the team for structure. We have software engineer, CAD engineer, and also manufacturing engineer. Next. All right, so this is the key parameters of Hebat 2 from Open Rocket software. The overall length of our rocket is 106. The diameter is 6.15 inch, and the total mass of the rocket, including the motor, is 65.5 pounds. The simulated apogee that we get is 10,651 feet. The center of gravity is located at 64.341 inch, and the center of pressure is located at 74.884 inch. The stability margin is 2.2 caliber, which actually satisfy the type requirement from 10.1, where requires to have 1.5 to 2.5 caliber. So we are within in that range of stability margin. And our maximum velocity is at 949 feet per second. Our off-road velocity is at 99.8, which is really close to the detailed requirement, which is a minimum of 100 feet per second. Next. So this is the vent hole location where we require to have an adequate venting in order to avoid too much internal pressure before we deploy. So we actually have received comment from Jim Jarvis. He advises on like adding more number of holes to our rocket in each section. So we decided on having 3 holes on each section for on our 4-1 F and booster, which in the size 0.18 inch. From the detect, they suggested on 1/8 to 3/16 inch vent hole, so which is 0.18 is within that range. And then we also have payload vent hole, which is 0.39 inch. And another hole is located at 4.2 for Avionics. They have 4 arming holes, which also act as vent hole, which is in the size 0.31 inch. And lastly, payload will have another hole, which is for the arming RBF hole, 0.22 inch at 4.1. Next. All right, so we, from fin flutter analysis, we get that at our simulated apogee, 10,651 feet, the fin flutter velocity is 2,215.18 feet per second, and our maximum velocity of the rocket is only 949 feet per second. So according to the detailed requirement as well, it is definitely higher than our maximum rocket velocity. So our fin would not most like will less likely experience the flutter. Next. All right, so yeah, for the screws and hairpins location, like as you can see, we have 5 sections: nose cone for 1, for 2, and F, and also booster. I labeled A for the screws location. The screws that we are using is M5 truss head screw, which in the length of mm, and we are using 6 screw for each section for inspired hexagon like placement, and each screw have a maximum load of 1 kilonewton. And our hairpin placement is I label as B, which is located at the upper part of the 4.2 and also at the upper part of F. The hairpins on 4.2 for main parachute, we are using 6 pins, and for drogue parachute, we are using 4 pins at F. So each hairpin is maximum shear strength is 76 pound-force. Next.
Let's see. Can I ask a question at this point?
Screw location.
Yes, can I ask you a question? Can you hear me?
Still at screw.
I'm not sure if you.
So we can't hear you.
You cannot hear me? No.
Hello.
Let me test me. Can you hear me?
I can hear all of you just fine.
Okay.
Okay, let me try one more time. Can you hear me at all? Hmm. I'm sorry. Can any of the group hear me?
Oh, okay.
I can hear you, sir, loud and clear.
Okay. Well, I'm.
Yeah, now it's good.
Let me try to ask one question, and maybe if the right persons can't hear, someone can pass along the question. One thing I'm trying to understand about the rocket design is how you are connecting the airframe tubes and the coupler tubes. And normally you would glue the coupler tubes to the airframe tubes and assemble the rocket that way. But it sort of looks to me like you're basically going to screw all the sections together. And so that the couplers and the airframe sections may be loose until they're assembled. So I was just wondering if someone could describe how the airframe sections will be put together and how you have verified that the number of screws that you are using is adequate for the structural strength.
All right. Okay. Actually, okay. I didn't include it in this slide, but I added on the other slide where I talk about the coupler. In each coupler, we have drilled our screw holes and we attach flange hex nut in that inner wall on the inner wall of the coupler using JB which is the steel reinforced resin. So that's how we are gonna provide the thread for our assembly, like the screws. Does that answer your question? And then what else?
Is the reason for that to make it easier to ship the rocket?
Wait. Does your question means that why we are separating them into parts? Like, does it help in terms of logistics? Is it?
Yeah, I'm just curious if that's.
Yeah, it does. Because we'll be shipping our rocket together with us, and it's so hard to bring along a 106-inch rocket, so we separate it part by part.
What was the technique that you're using? Did you use the same technique for your rocket last year?
Technique is, you mean the methodology of layup,
Yes.
or? Oh yeah,
Yes.
we're using wet hand layup for the airframes. Just the same. We're using fiberglass and epoxy resin as the composite materials. Actually, we can go ahead and move the methodology slide actually, so I can explain further.
Okay.
Next. See, okay, I think the slide still stuck at the same. Okay. All right. To answer the methodology, or do you like where's the methodology?
All right, so to answer your question, the assembly methodology is same as last year. In order to make sure that each couplers and airframes are connected tightly, what we do is we actually epoxy the nuts on the inner wall of each couplets so that it will ease the entire assembly process so that we just have to screw it from the outside. And we have tested it with multiple mock assembly here. And so far, so far there is no issues on that. And the main reason why we came up with this assembly process is because number one, we are traveling from Malaysia to United States. We have to bring it in parts securely, and to ease the entire logistic process, we have come up with this idea and also this assembly methodology. Does
Okay,
that
thank
answer your
you.
question?
Yes.
I'm so sorry for all the inconveniences over here because we have some issues, technical issues.
Yeah, I would just recommend that in your you know, as you go on presenting the rocket design, that you might include a discussion of how you have how you put the sections together, because it's probably different from what most other teams will do. So that's something that you should kind of show some pictures of, and how you are assembling the sections.
All right, so actually that will be explained in the later parts of the slides, but since you have asked it earlier, we explain it earlier.
Okay, so you can go ahead.
Maybe we'll show you a picture of this assembled version of the rocket later.
Okay.
All right, moving on, this would be the rail button size and location for our rocket. It will be placed in the aft and booster section, and the size is 1515.
Yeah, I had one question on the rail buttons. I was sort of expecting to see that they would be secured in your centering rings, but it doesn't appear that that's the case. I just want to recommend that the rail buttons be very secure on the airframe, and I'm pretty sure you're doing that, but just make sure that the buttons are very strong.
Yeah, so the assembly mechanism is also as same as last year. What we did, the inner part of the rail button, we epoxy it so that from the outside, we just screw in the rail button. And so, based on last year's experience, the rail button never came off. So we are actually applying the same methodology.
Okay, is there a hardware attachment of some sort inside the airframe itself? Some backing, or you know, what you don't want is just to depend on the airframes themselves. You want to have something with more strength inside the rocket that holds the rail buttons secure.
Okay. So shall we now change it to attachment? Shall we not change the attachment of the rail button to the centering ring, or we can still remain by epoxying the inner part of the rail button?
Okay, I've just seen many cases where a team, or just anyone flying a rocket, they load the rocket on the rail, and then a rail button comes off, and it's not a good time for that to happen. So you just want to make sure that it would be very difficult to accidentally pull one off, or have some damage like that. That would be bad.
Yeah, I think what you can do is on the forward rail button, it's really close to what I'm seeing is a coupler break between the aft and the booster tube. Maybe if you shift it down a little bit, instead of having it pass through just one airframe, you can double the thickness in which the shaft of the screw passes through. So you would pass through the airframe and the coupler. And for the rear section, you could pin it to the centering rings. But then again, these rail buttons they're not really taking the full weight of the rocket while it's resting on the pad.
Let me correct that a little bit. Is one of IREC's rules is the lower rail button must be able to support the full weight of the rocket while on the pad.
Oh, okay.
Okay.
All right. So, Van Mita, please take a note of that.
Yes, I'll find the rule number for you. Give me a second.
All right. Thank you.
We'll look into it and make the necessary changes. But then right now we have actually completed the airframes and everything. And we have submitted the technical report. So will there be any effects if we change the locations of the rail buttons later on? Because I'm afraid that it would affect our technical report information.
I wouldn't be I wouldn't be concerned about that. I think what we just want to make sure is that the buttons are as strong as possible.
All right.
And if it's slightly different from what's in the technical report, then I would just say that, you know, you explain the change by just saying that you're going with a you know, a stronger attachment if you can do that, and I don't believe that will be a problem. I think, you know, you still have your rail button placement. You can still move the forward rail button backwards and still have an acceptable arrangement of the rail buttons. I would probably not have them closer than perhaps 24 inches, but I think you're saying 32 inches, so you have room that you can move that forward rail button if you can find a more secure location for it.
Let me add, my observation is that the failure of the rail buttons happens most often when you're loading the rocket and it's inadvertently twisted out of alignment, putting undue stress in the rail button in a direction you're not expecting.
Okay.
So anticipate some stress in that direction, but also make sure your team knows to be very careful in loading the rocket on the rail, because there's a strong chance of wrenching off a rail button.
All right. We'll take note of that.
Yes, yeah.
Can we move further? I mean, can I like proceed with the further presentation? Is there any other comments that you'd like to add on?
I think you can go ahead with the presentation, but let me make one quick comment. And that is to recommend, I'm not sure where you got the rail buttons from, but 1515 rail buttons sometimes don't fit the rail very well. It's just a characteristic of 1515 buttons. They can be a little tighter. So one piece of advice I would give you is that early on, you make sure that your rail buttons fit the rails that you'll be using. And I've seen many times where a team has to sand a rail button at the last minute in order to get it to fit. So I would just recommend that early you do a test fit and make sure that your rail buttons will fit the rail.
Yeah, I think on this matter paper, I have to mention the sizing of the rail button, because we are using ESRA provided rail launch rail. So Spaceport mentioned that the rail button size is 1515.
That's correct, but not all 1515 buttons purchased commercially fit the rails. Sometimes they don't fit, and you should check that.
All right. So the next one would be on the markings. We have followed the DTEC requirements. The team ID is on the booster section, and yeah, followed by the rocket's name and affiliations.
Is that a picture of the actual rocket?
Yes, sir, correct.
That's a beautiful job. Very
Great.
nice.
I like it.
Thank you.
All right, let me proceed with the methodology. So here is the calculation compiled in this table for our fabrication. So this is the fiberglass to resin ratio that we are using. For nose cone and coupler, we are using 1 to 0.7 fiberglass to resin ratio. And for airframe, we are using 1 to 0.8. And while for the resin to hardener ratio, we are using 100 to 28.4. The type of epoxy we are using is laminating resin and a slow hardener for our laminating process. Next.
What kind of epoxy did you use?
Laminating epoxy.
What brand?
Oh, what brand? Epoxamide. It's epoxamide.
Okay. I'm not familiar with that epoxy,
Okay.
but which is not a problem. I'm always concerned about epoxy and the high temperatures in New Mexico.
So can I proceed? Okay, so like this is the design of our nose cone. We are using the metal tip, and the nose cone shape is 1 Karman's profile. The length for the metal tip is 2.72, and the nose cone is 17.28 inch, which make the overall nose cone length is 20 inch. And we added a shoulder to our nose cone for mainly for our payload integration and also to secure it to our 4.1 FM. And then the 1 Karman's profile, we are using this formula, and we use our MATLAB to produce the coordinate. So this design is designed by ourselves. When we take the coordinates, when we send the coordinates to make it a 3D design, we send to the our partner industry to make a mandrel out of it. And then we proceed on making split mold for our nose cone. So that's our methodology for fabrications. Yeah. Next. So as I said, we are using split mold method because we want to maintain the profile of our nose cone, and we find that split mold have a better accuracy in terms of um, maintaining the profile. So it's just a simple layout process. We apply the releasing agent to the split mold, and then we use the wet hand layup to make the composite materials, and then we actually wait until it's tacky. As tacky means it's partially cured, like gel state, and then we trim the excess. After we trim the excess on the mold, actually we join the split mold together and screw it from the outside, and then we apply fiberglass strips to secure and to cover up the split joint. And then the post-cure process, we just demold it and then finish off with sanding and trimming to make the nose cone. This is how it looks like. Alright, so for the airframes, we have four, for 1, for 2, aft and boosters. So this is the dimensions. For 1 is 18 inch, for 2 is 17 inch, aft is 20 inch, and the booster is 29.4. We are using 10 plies of plain woven fiberglass for our airframes, and the outer diameter of our airframe is 6.15 and the inner is 6 inch. And they are connected by the shoulder from our nose cone and also 3 couplers. And we are secure the airframe together by using 30 and 5 truss set screws and also with the shear pins as I said just now. Next. Next. Purna, do you have any question?
Nope.
All right, thank you. So this is the methodology of the airframe. We actually designed the setup ourselves, and we using the rolling layup method, and then just we apply we use a cylinder mandrel which have a 6-inch diameter, which made the inner diameter of our airframe, and then we put PTFE layer, which it's also like a releasing agent, so we can demold it from the airframe, the cylinder easily. So the method we are using is just the wet hand layup technique. And yeah, we just roll the 10 layers of fiberglass. And then finally, we wrap it with pre-ply. Pre-ply acts as like, it's a fabric that absorbs excess epoxy or resin, which makes sure the surface finishing is smooth. And the post-cure process, which is after we leave it to cure overnight, we just demold it, and then we use the lathe machine to actually cut the airframe to sizes precisely, and then we also sanded the inner of our airframe to make sure our couplers slide in smoothly, just to, you know, add some tolerance there. Any question? Okay. No. So this is our coupler. Our coupler size is 12 inch, which in the detect requirement, it says that we have to make sure the length is at least 1 body caliber. So our inner diameter of our airframe is 6, and then we times 2 is 12 inch. So the diameter is 6. The thickness of the wall is 0.09. And yeah, we tested tensile strength for our coupler, which is 0.5 kilonewton. And yeah, we have 3 coupler, which is 4, and avionics for avionic integration, and booster is in between aft and booster. So the build methodology is pretty much the same as nose cone. We're using, but we are using a cylinder mold, aluminium, which have the the outer diameter of coupler, which is 6 inch, and then we make the mold, spray mold out of it, and use the same method of wet hand layup. Wait till steady state, and then trim, apply strip to make up with the joint, and then left it to cure overnight. After that, we demold and trim the edges. As you can see here, we are using JB Well brand steel reinforced resin to secure our flange head nut into our inner wall of our coupler. Why we use the flange head nut is because the flange actually add more gives more surface area for the resin to attach to. So we find that it's better than a regular hex nut. So far, question? If no question, then next slide. All right, so this is the fin and the bracket design that we came up with. Since we are using the detachable fin method, so this is the fin. The fin is made of E fiberglass G10. We bought it from locally from Global Holdings Sdn Bhd, and the yield strength is 310 megapascal. The bracket is made of aluminium, 6061T6, also partially sponsored by our partner industry, GE Metal Engineering Works. And the yield strength is 475 megapascal. The methodology for both fin and bracket, we just send it to our partner industry, and they are using CNC milling machine to make our design. And yeah, so you can see the bracket that we made actually on the horizontal part that is attached to the airframe have a slight curve that contours that follow the curve of the airframe actually, just to reduce the gap that possibly made by a regular bracket. And then yeah, to secure the fin and the bracket together, we're using flange hex screw M5 size. Why we use a flange hex is because the flange acts as the washer, so we don't really have to, you know, add washer. So yeah, to ease the assembly process. And then to secure the screw, we're using nylon insert lock nut because the special thing about nylon insert is that it adds up more grip than a regular hex screw. And then lastly, on the horizontal part of the bracket, which are attaching to the airframe, we're using a flathead screw, countersunk, and these are the max load as stated. And the materials that we are using are stainless steel for all the screws. All right, so this is just the overview of the detachable fin. As you can see here, this is the booster part of our rocket, and we actually have 4 centering rings, but in this slide, I just want to show the mechanism of the detachable fin, where three metal centering rings are involved. As you can see there. Yeah, how we attach it is just by using screw, flathead screw to the centering ring, and the centering ring have threaded inside of it, like yeah. And then yeah, why we choose to make it detachable is just to ease the logistic and also to add versatility to the design for any possible future development. The centering ring also, wait, I forgot to mention, the centering ring also secured to the booster airframe using truss head screw. And the maximum load is 1 kilonewton. So, all right, so yeah, based on what's available in our composite lab, this is the tensile strength test machine, and we managed to do sample test for our composite materials. And for nose cone, since we are using split mold method for fabricating it, also the couplet. So our main concern is the joint area. So we make a panel of composite, and we copy the same joint method on that, like on the panel, and then test it on the machine. So for the nose cone, we have 4.3 kilonewton, and the coupler is 0.5 kilonewton tensile strength. And for the FM is 21 kilonewton, sorry. Okay, so we, for fin load test, actually, we in our university we don't have that much machine like required to actually test the fin load, and also we don't want to risk to damage our centering rings. So we use structural analysis instead. So on the left side, that is the distribution of stresses for the fin bracket, and on the right side is just the resultant displacement of the fin bracket. And then from our calculation, the lift force that we obtain from maximum dynamic pressure with half rho v square is 90 Newton and for our flight. And then we add factor of safety to 3, and yeah, we test it, it's 270 Newton, if I'm not mistaken. So we apply that load with that safety of factor, and we get the maximum stress that it will withstand is 30.8 megapascal, and the maximum displacement is 5.5 mm. So yeah, to conclude with this structural analysis, we know that our fin yield strength is 310 megapascal, and our bracket is 275 megapascal. So since the actual and the maximum force that we're experiencing during the launch is only 90 Newton, 90 Newton, which makes sorry. No, the maximum stress that we get from the factor of safety 3, which is less than the yield strength for each material that we are using actually. So yeah, it most likely won't happen. So find it safe. Any question? Question? If no question, next slide. Thank you.
Right, so that's the end of for the structural subsystem. Before I proceed for the payload subsystem, is there any question for the structural subsystem? Yes, regarding, I would like to answer your question for the fin brackets, the fin load testing. Since earlier we had a shortage of, in terms of resources and all, so what we did is we now managed to out another set of fin panels. So it just arrived yesterday, so we were testing out the fin load test latest by tomorrow and get the results out of it to determine what is the maximum load that each fins and the fin bracket can withstand. Right, I'll pass it to Hafif, who is the team lead for Payload, to start.
Okay, hi guys, good evening. My name is Muhammad Afif and I am the team lead for the payload subsystem of Hebat 2. So let me introduce my team first. We have our system engineer, CAD engineer, I am the payload lead, and electronics and manufacturing engineer. So for the payload side of things, we'll focus on the detect requirement, the first one. And next we'll focus on the mission, design and test that we have done so far. So for the detect requirement, the payload team have met all the 5 requirements set in the detect. The first one is our payload have achieved the 8.8 pounds required in the detects. The second one, our payload is independent payload functionality, which means that this year we are conducting our scientific experiment. So our payload is not just a boilerplate. That's the second one. And the third one is location and interference. So our payload is independent to our launch vehicle system, which means that our payload can be separated separate with not connected to any other structure or airframes. And the fourth one is restricted material. So our payload did not have any like hazardous or bioactive material inside it or any animals inside it. So we have met the fourth. Okay, the next one, our payload is the TU CubeSat. So next, so our mission. So we have three main missions for the payload. The first one is measure, like Vamita said earlier, measure the initial value of rocket. Second one is store data inside and transmit to the ground station. And the third one is to record the flight footage. So to achieve our mission, we have three main components in the payload, which is CubeSat, and Pixop will be our payload, and we have a camera compartment below the payload. Next. So the design, this is our payload general specification. Our payload is made from 2020 aluminum extrusion profile. And then we have, then followed by 3 stainless steel and 1 aluminum side plate will be attached to the side of the aluminum profile. So this will make our payload mass is 4 kilogram or 8.8 pound, and the dimension will be 3U. So on top of that, the side plate will be engraved by sponsor and contributors' name and logos. And we also have a 2 FPV camera inside our camera compartment. So in terms of airframe integration, the whole payload bay will be secured to the airframe by using M8 thread rod that coming from Noscon metal tip down to the butt plate. So the payload bay itself, payload and the camera compartment, it will be secured by using 2 M5 thread rod. And we also consider
All right, so we are well aware of the time since the structure subsystem took more than 45 minutes. So we now skip the payload subsystem and we jump to avionics.
Hi guys, can you hear me?
Yeah, okay.
Right. My name is Amirul, the Avionics lead of Avionics subsystem. We have consists of 4 members in electronics engineer, 2 electronics engineer, and 1 CAD design engineer. So let's talk a bit brief on the detailed requirement of avionics. First of all, we have the GPS tracking requirement. So focusing on frequency management, recommended cost GPS tracker options, international team, getting the ham license, frequency assignments, GPS safety inspection, final GPS system checkout, and GPS system review. So for the 4.1, 4.3, 4.4, and 4.9, we have completed that. And the 4.10, the frequency assignment, we are still waiting for the frequency assignment right now. Will be assigned by DaVinci MCC. And for the 4.11 and 4.13, especially on the final GPS system checkout and GPS system review, we are going to done these two system checkout later during the safety review and also during in the launch pad later in the Space for America Cup. So that's about the detailed requirement on GPS tracking system. Moving on to number 6, which is the recovery system in avionics. So we have to cover on redundant electronics, redundant COTS electronics, cable management, secure wiring connections, ground testing demonstration, energetic safety in arming, arming device access, and arming device location. So the 6.8 until 6.13, 6.19 and 6.20 are completed. We have done this and except the 6.12.3 regarding the strain relief, because we are quite confused on that, but let's talk about it later after we have finished the presentation. And also the 6.18 regarding the energetics, we are using black powder initially, so we haven't have the set black powder and we are going to purchase the black powder in Space for America Cup later. And going for the Appendix B safety wiring guideline, we are going to talk about the hazard identification regarding the battery, the wire type of wire you use, a wire strip or crimp method, soldering wire terminal, use of binding screw terminals, electronic fixtures, and battery mounting position. All of these methods that we have implemented inside our avionics bay, and we have successfully completed on all these safety wiring guidelines Appendix B. So next slide.
Please slow down. You're going too fast.
Next slide. All right, this is our avionics bay. As you can see on the image on the screen, is actually the rendered image of the avionics bay. So basically, the Avionics is secured inside the Avionics coupler mentioned by the structure lead Farhana just now. So on the Avionics bay design, as you can see, we have the slat, this blue slat with 4 sections. So that we use the 4 sections so that we can have a lot of room, and also we can manage, we can have an easier cable management, so that for each one section we can put one specific altimeter, then we can simplify the wiring for each section. So we are using 2 quartz altimeter. The first one is the Mesoworks RRC3, and the second one is Altimetrum Easy Mini. Actually, we have bought this altimeter last year and we have used in the previous launch, and they work perfectly. We really love the reliability of the data and also the ejection that they produce. For the GPS tracker, we have the featherweight GPS tracker. We are using the GPS tracker. And for each altimeter, the Altimetrum Easy Mini and the Mesoworks RRC3, they are going to be supplied by 9-volt battery as the main power supply. And also the 9-volt battery is going to be secured by its holder, and also will be going holder. And also it's going to be cable tied as well to secure it from the lateral movement. We also have the terminal blocks that connecting all the wiring from the altimeters and also to the e-mesh. So basically the wires are, basically the drope and the main terminal of the of both altimeters, the wires is going to be connected to terminal block. And on the other side of the terminal block, we are going to connect the e-mesh later. We have the screw switch bracket is going to secure our screw switch. We designed this because we want to make sure that the screw switch can be accessed as close as possible to the airframe. So that's why we designed this. And also we had the mounting bracket at the bottom side actually. And also on the on the both brackets, we have mounted the M10 eye bolt with hex nuts inside there for the attachment of short cords later, for the parachute attachment. And also for the whole Avionics bay, they are secured by using 2 M8 threaded rod and hex nuts as well, and also washers. And on top of those bracket, as you can see in this image, we have the G10 buck plates. We have 2 different buck plate for each mounting bracket of each bracket. The inner one is the coupler buck plate following the dimension of coupler inner diameter of the coupler, while the outer one is the body tube buck plate, where follows the inner diameter of the body tube. And finally, we have the chargeware that is going to store the black powder for the parachute ejection. So on the left side is going to be the drope side for the parachute ejection, and the right side is for the drope parachute, and the left side is for the main parachute. So next slide. Sorry.
While there's a pause, I have a question.
All right.
Okay, what will hold the powder in the charge wells?
Basically, we are going to insert the powder inside the chargeware. Then after that,
Yes.
we are going to cover it with the recovery wording that we made it by ourselves. And after that, we are going to seal it using tape and make sure that the seal is really tight. Then we can shake it, the Avionics bay, make sure that the black powder is not coming off from the chargeware.
Very good. Make sure it's tight, because I've seen several flights where the powder came out of the charge well and there was no ejection, causing a big problem.
All right, I will take note on that.
Yeah. How will your igniters go into the charge wells? Will they be fed from the top into the well, or are they coming through the bottom through your bulkhead?
It's going to be from the top. Basically, you are going to connect the EMI from the terminal block, and there is going to be a hole that we can access from the terminal block to the top section. Then we are going to insert that inside the charge well.
Excellent. How will you seal that hole that the wires pass through?
Basically, we are going to use tapes, a lot of tapes, to make sure that there is no air or heat coming through inside the electronics part. And yeah, that's what we are going to do.
Okay.
All right, so here are our COTS altimeter. So as mentioned just now, we are using two COTS altimeter, Miserworks RRC3 as our primary altimeter, and the Altispectrum Easy Mini as our backup altimeter. So for the primary altimeter, yes, the drogue chute is going to be ejected on the at the apogee, while the main parachute is going to deploy at 1,500 feet upon descent. While the backup altimeter, we are going to put a 3-second delay, which means that once the Miserworks RRC3 has deployed, has ejected the black powder for drogue chute, 3 seconds after that, the Altispectrum Easy Mini is going to eject the black powder 3 seconds after that. While the main chute, they are also going to deploy the black powder ejection for the main chute at 1,500 feet as well. So on the, as you can see on this image on the bottom side, you can see the wiring diagram of each altimeter. Each altimeter is going to have its own circuit, which means it has its own screw switch. It has its own 9-volt battery. It has its own E-mesh that connects. Basically, for one altimeter, there is two E-mesh, which is one for the road, one is for bin. And also it will be having its own wiring system. So this is the redundancy system that we have to follow as per in the DTAC requirement. So next slide. So this is the featherweight GPS tracking system, the GPS tracker that we are going to use inside our Avionics Bay. So the featherweight GPS tracking system is actually, we bought it actually last year, and we have used it during our previous line, Hebat 1.0, and it works successfully. It provides the correct latitude and longitude of the rocket after it launched, after it landed. So by using the latitude and longitude of the rocket, we use it, and yeah, we found our rocket easily. And also, the featherweight GPS tracking system is running on 915 megahertz frequency. This is because we are unable to obtain the ham license that could enable us to operate on 70 cm frequency band. Actually, in Malaysia, we can apply for the ham license. However, there is no reciprocal agreement in between ham Malaysia of ham license in Malaysia and United States. So in any way, we cannot use the 70 cm frequency, unfortunately. So the featherweight GPS tracker, we are going to power up the featherweight GPS tracker using the 800 milliamp hour LiPo battery. The recommended one is just 400 milliamp hour. That could last almost 5 hours of flight. But we are just beef up a little bit, going for 800 milliamp hour, and we have tested that the tracker is able to operate up to 7 hours non-stop. By the featherweight ground station, we are just using the provided 2 hours LiPo battery, and it's going to be connected to iFib app for data display, as you can see on the top right image. So apart of having the COTS electronic, which is the COTS altimeters and COTS GPS tracker, for this year's launch, we are developing our extra altimeter, our own altimeter. It features accurate and reliable flight data. And also we are going to have a live telemetry data transmission from the tracker itself, from the altimeter itself to the ground station. And we are targeting that this altimeter development cost, having a low budget development cost. And as you can see on the image, the top left is the rendered image of the X-ray altimeter. So we have the barometer sensor, accelerometer sensor for recording the altitude and temperature and the change in angle of speed of the rocket. We have the ESP32 microcontroller that managing all of those data. We have the LoRa module that we use, the 950 megahertz LoRa module to send our telemetry data to the ground station. Apart from that, you also have this SD card module, not to save the data should the LoRa module fail. At least we can retrieve the data after the flight. On the top right corner, you can see this actually a GUI, the graphical user interface that we have developed to read all those data transmitted by the
Amirul?
Yeah.
Yeah, I think just want to wrap this section for asteroid altimeter. It will not affect the recovery system of the rocket. Therefore, I think with your permission, can I skip the slides, sir?
Yeah, sure.
This is actually fully an independent altimeter that we are developing on our end, just to do some sort of live transmission to the ground station on the launch day. So if you have no question, we can go ahead.
All right, okay. So just to talk a little bit on the structural components of our Avionics bay, we have the slab. It is a 3D printed one. We use the material PLA, and the weight is 0.725 pounds. And the mounting bracket and the screw switch bracket is also 3D printed, but we are using the different material, which is PETG. It has this almost the same strength property with the PLA, but it is quite stronger. And that's the 3D printed part of the Avionics bay. Next slide. We also have some other parts like threaded rods that connecting all of the Avionics bay assembly. We are using stainless steel A4. We also have the eye boot for the shortcut connection, also stainless steel. And we have our buck plate, like I mentioned earlier, the body kit and the coupler buck plate set. The material is G10 fiberglass. So next slide. All right, so we have done the COTS electronic test as per requirement in DTAC. So the first one is the COTS altimeter functionality test. We put all the our RRC3. We have two RRC3 and two EasyBini connected to on both terminal for drogue and main terminal, and we put it inside vacuum chamber and we test it up until 11,000 feet of altitude, simulated altitude, and we gonna see whether they can successfully record the data or not. So the result shows that the Easy Mini, we have two Easy Mini 9363 and 9350, have the FPG recorded 11,209 and also 11,240. While the RRC3 have a little bit lower altitude value at 11,187 and 174 feet. Also on this video, you can see the delay of the Easy Mini ejection on the drogue. Basically, it follows the setting that we have set, which is the 3 second. So it works flawlessly. That's about the COTS altimeter functionality test. Moving on, the altimeter battery interest. So we just want to make sure that we've supplied the altimeter with 9-volt batteries. We just want to make sure that they can supply adequate power of the altimeter even after 2 hours of running in pad mode. And just as a result, the voltage difference. So basically, by using a new 9-volt battery, the voltage of that 9-volt battery should be around 9.4 or 9.5 volt. So after running for 2 hours, as you can see on the result, the Easy Mini consume around 0.3 to 0.5 volt, while the RRC3 consume a little bit more, from 1 to 1.2 volt. But the minimum voltage required by both altimeters is just 3.3 volts, so it is more than enough to power up and the altimeter during the flight and also performing the ejection. So the final COTS electronic test that we have done is the GPS system battery drain test. This is because we have changed the recommended from 400 mAh to 800 mAh we just want to make sure that the battery can supply just enough. The GPS battery. The battery can supply enough runtime for the GPS system. So we have run for 7 hours, and the result is the GPS tracker consumes around 0.5 volt of battery, while the ground station is 0.1 only. So if we charge full, the LiPo battery is going to be around 4.0 volt. And after 7 hours of running, we just the battery voltage for the GPS tracker is around 3.5 volt, which is higher than the minimum voltage required, which is around 3.3 volt. So that's all about the Avionics system for the Hebat 2.0. So I would like to open for any question from you guys.
I have no particular questions. Your system looks pretty good so far.
All right, thank you, sir. We'll move on next to the recovery system.
So, hi everyone. My name is Srihari and I'm the lead for recovery sub team. And in our team, we have a CAD engineer and also a manufacturing engineer. So for the DTAC requirement, firstly, the dual event recovery involves an initial deployment and also a drogue parachute deployment. And so our recovery system will have a drogue chute deployment at the apogee, and also the main chute deployment will happen at 1,500 feet. moving on to the next one. Appropriate descent speeds under drogue should be between 75 to 150 feet per second, and our drogue's descent velocity is 60.2 feet per second. Next, the main deployment event for a recovery method shall occur at an altitude of no higher than 1,500 feet. So, and also it should reduce the vehicle's descent rate to below 30 feet per second. And our main descent velocity is 24.5 feet per second. And for ejection gas protection, we have prepared recovery warding to reduce the residue from the black powder. And moving on to the next one, which is the parachute swivel links. We'll be using proper rated carabiners and shock cords. And for the parachute coloration and markings, we have followed based on the DTEC requirements. Next slide. Yeah, so as you can see, the recovery warding, we are made it by using kitchen towel. We basically soaked in mixture of water and sodium bicarbonate and dried it under the sun to create our recovery warding. And as you can see on the right, we have tested our warding and it reduces the burning from fires and everything. And next for the previous slide, please. And for parachute protectors, we'll be using the top flight recovery parachute protectors. And the size that we'll be using are 30 times 30 inch. And as you can see on the right, this is the way that we'll be packing our drogue chute and also our main chute.
Can I bust in for a moment?
Yes, sir.
Yeah, I'm concerned about the way you're packing your chutes. To have things wrapped around like that is not something I see very commonly. I would subject myself to Jim on this. Normally, one would like to pack the chute so that everything can come out in a linear fashion when ejection occurs, rather than have things wrapped, which can make them tangle more often.
Yeah, I understand, sir. The picture are just for illustration, but in reality, we won't be wrapping the shock cords around the parachute. Instead, it will be both the shock cords will go to the U bolt and I bolt on
Okay.
Yeah.
Yeah, like the zigzag I see there. That looks much better.
Yeah.
Yes, thank you.
Okay. So moving on, we'll be using carabiners, which is made from 304 stainless steel, and the length of it will be 3 inches, and the size is M8, which is around 0.3 inches, and the braking strength of the carabiners is 937 pounds. And for the shock cords, we'll be using tubular Kevlar, and we'll be using different lengths of shock cords, which are the 20 feet and also the 10 feet. And the width of our shock cords are 7 over 16 inches. And the braking strength of the shock cords is 5,300 pounds. And as you can see on the right, that's the way how we'll be folding our shock cords. Next slide. All right, so for concept of operations, our ConOps contains 9 main mission phases. And firstly, you will begin with pre-flight setup. And then the second one will be launch pad setup, moving on to the ignition setup. And after that, the fourth one will be liftoff. And after 4 seconds, the propellants will be burnt off. And the fifth step, it will go into the coast phase. And sixth, it will arrive at apogee and the drogue deployment occurs at apogee. And when the rocket descends to 1,500 feet, the main will be deployed. And finally, the rocket lands safely. Next slide. So this is the build methodology of our main parachute. Our main parachute is basically made from ripstop nylon fabric, and we use the CD of 1.5, and the diameter of our parachute is 10.3 feet. Next slide. So this is how we made our main parachute. So firstly, we cut the fabric to rectangular shapes, and then we cut it into triangular shapes based on the dimensions that we needed. Next slide. Then we sent our the pieces that we cut to the tailor for them to sew all the pieces together. And then we brought it back and cut a spill hole. And then we sent it back to the tailor to sew the shroud lines, attachment points, and also the spill hole. Next slide. And finally, we sent it to the logo printing vendor for logo printing. And finally, we attached the shroud lines to the parachutes. And so for the drogue chute, we'll be using last year's drogue chute, which has a diameter of 4.2 feet. Next slide. So the tests that we carried out are ejection tests. For drogue chute tests, we used 3 grams of black powder for successful ejection and separation of the body tubes. And just as a reminder, the black powder that we used are self-made in Malaysia because we are not allowed to ship it from the United States. So we had to manufacture our own black powder. And for the main chute test, we used around 9 grams of black powder for successful ejection and separation of the body tubes. Next slide.
Can I bump in for a moment?
Yeah, sure.
9 grams seems like a large amount by American standards. I'm wondering if your powder is as powerful as what we have here.
Yes, about that. So our quality of the black powder that we manufactured will be lower compared to the one that we'll be using in the United States. So that is why we had to use quite a high amount. Yeah.
Will you be making adjustments for that with the American powder?
Yeah, because we'll be carrying out ejection tests over there also before launching.
Good.
So yeah.
Excellent.
And finally, we also did the parachute opening test. As you can see, we did the drogue opening test and also the main opening test to ensure that the parachute inflates completely when deployed. So that's all from recovery. Thank you. Any questions, sir?
Yes, I have quite a few questions on recovery. And the first comment that I will offer is that it seems to me that your drogue parachute may be too large, and I'll just give you my opinion on drogue chute sizing. I think you were saying the descent velocity was about 70 feet per second, which
so our drogue chute descent velocity is 60.2 feet per second.
Okay, that's pretty slow. Generally speaking, I would be recommending velocities just calculated based on the parachute statistics of maybe 80 to 90 feet a second.
All right, sir.
The reason that I would recommend that is with a descent rate of 60 feet per second, your rocket sections are going to be pointing straight down. They're just going to be hanging under the drogue chute. And that means that when you put your main chute out, it's going to be much easier for the main chute to foul because you're putting, you're ejecting the main parachute straight down. Ideally, what you want is for the descent rate under the drogue to be faster so that the rocket sections actually fly outward a little bit. You're looking for a shape that's oftentimes referred to as an inverted V, where the descent rate is fast enough so that the sections don't point straight down, but rather they fly out at an angle. And the objective of that is then when the main chute comes out, it's more likely to be able to come out and not foul with the rest of the rocket when it comes out. So I would suggest that you get with Julian and talk about the descent rate and maybe consider reducing the size of the drogue chute if that's still a possibility for you. Generally, I think it is better to go with the drogue that is too small than too large, because if the drogue chute is too large and the descent rate is too low, then you'll almost surely come up with this the fouling of the main chute when the main chute opens. And it's particularly difficult to overcome that with rockets that have the payloads, because the top section tends to fall straight down because the payload tube is heavier, and so this is a problem that is fairly common. So I would just suggest maybe looking at the drogue descent rate. Do you have any comments or questions on that topic?
I have a question
Yes.
to add to that, just to make sure that your drogue chute is towards the aft and your main chute is towards the fore end of the rocket.
Yes.
Which it is, yeah.
It is. Okay, thank you.
The drogue will be at the will be coming out from the aft and also for tube
Okay.
2. Yeah.
All right, thank you.
Okay, go to the slide that you showed that had the packing of the chutes. Okay. I know I've made this comment in several of my reviews, and I'm going to make it again, and that is about considering the use of a deployment bag for your main chute. Your main chute is very large, and my experience, when you get beyond a certain size of a parachute, you really should be considering the use of a deployment bag to help organize the deployment of the chute. And I'm just wondering if you have looked into that. Have you investigated using a deployment bag, and what are your thoughts on that?
Yeah, so about the deployment bag, basically, we don't really have an experience on using a deployment bag, and also our mentor doesn't really have an experience. So we are pretty unsure about how we will be using the deployment bag. But we have not checked on the sizing of it yet.
Okay. Yes, deployment bags are can be done in different ways, and and I would imagine that it is a little bit confusing about exactly how to use them. One comment I would make for the size of the chute that you have, and for the likelihood that the airframe is going to be pointing downwards, I would just say, and I'm just to be honest about it, I would say that the chances that the main chute will deploy properly, I would say is maybe not better than about 50-50. And so it might work and it might not work. If you use a deployment bag with a chute that size, I would say that your odds increase to about 95%. It's that big of a difference. And I do in the US, I do the level 3 certifications for Tripoli. And so I know that over time, one of the main reasons that level 3 flights fail is because of failures of the main chute deployment. It's very common, and sort of conceptually, the reason for that is that people have experience with smaller rockets and using the cloth protectors like what you're using. And they try to continue to use that same approach as the rockets get larger and larger. And at some point, and it usually occurs at around a 4-inch rocket, all of a sudden the main stops deploying properly. And you just have to go to a deployment bag in order to get more reliable deployment. Deployment bags are not difficult. If you wanted to talk about them, I think I can give you some suggestions for what you might, how you might go about doing a deployment bag if you have room and a little more room in the rocket to use them. But the purpose of a deployment bag is to organize the deployment of the chute. When you have the chute just wrapped in a blanket like that, the blanket will come off, and then basically the parachute it's not organized at all. It's just there, and it hits the airstream, and it just sort of opens randomly. When you use a deployment bag, it helps to organize how the deployment occurs. And so the first thing that happens is the shroud lines get pulled out of the bag and they get extended. And then the bag gets pulled off the parachute. And if this is done in combination with what's called a pilot chute, that opening occurs with the parachute vertical, not in some random direction. And so it very much helps to make a large parachute open in a more organized manner. And it also delays the opening of the parachute slightly because it takes some time. I'm not sure if I can give you a full explanation now, but the pilot chute will pull the deployment bag upward, and then once the harness is completely extended, then the parachute gets pulled out. And that provides just a few instances of time for the parachute to get above the rest of the rocket. So there are those two benefits that are just really very important for organizing the deployment of the parachute. And I think you could increase your chances of success if you used one. And so I'll just leave it at that. I don't know, Jimmy, if you have any comments on that topic.
Well, I'm not a user of rocket bags, but after hearing you and watching Rocket Man pack one, I think I'm a convert.
Okay, sure, sir. We'll look into that.
Yes, if you would like, I can send you some suggestions on how to do it. If you don't want to change, then I won't. But I'll help you if you would like some additional information.
Jim, how much more internal volume does the deployment bag take compared to the standard chute protector? I'm pretty sure they have ample of space inside, but I was just curious.
Well, it depends upon the bag that you get. What I would say is if you have the ability to make your own bag, and if you have Nomex, it does not have to be thick material. Some commercial deployment bags use fairly thick Nomex, and that can take some room. So that's actually something that I'm looking at right now, but I might be able to make a recommendation. The amount of material is probably not much more than what that is being used for the cover now. So if you have a little bit more room, you would be able to fit that in. There also needs to be a pilot chute added to the top of the bag, but it usually is fairly small. It's maybe a 3-foot diameter, and it just sits on top of the deployment bag. But if there's the you know, I will just emphasize that it makes such an improvement in the reliability of opening a large chute that I would just strongly recommend that you at least look into it and see if it's something that you could do and if you would want to do it.
Okay, thank you.
All right. That's it for the recovery part, and I'll move on to the propulsion part. But before that, Jim, I would like to ask you, do you have any sort of videos that shows the deployment bag assembly methodology? Like we really have no idea on how that actually works.
Well, I have a video. I think I sent you a link to it. I call it the Narcon video. I'll send it to you again. It goes through some of the reasons for using a deployment bag. I wouldn't tell you to do it exactly as I have in that video, but it would provide some good context for you on how to do it, and I can resend you the link, and I can tell you what parts of it are applicable and what parts might not be.
All right. Okay. That works. Thank you. All right. We move into the last session of for today, which is propulsion.
All right. Hi, everyone. Can you guys hear me? All right. So, hi, everyone. My name is Rishi. I'm the propulsion lead for the Hebat 2.0. And in our propulsion team, we have CAD engineer and as well as manufacturing engineer. So next slide. So for the detect requirements for propulsion, we have already satisfied all three of them. The first one is the COTS motor. We'll be using M2500T, and it has been listed in the NRC website, so it's approved by the NRA. And also the next is non-toxic propellants, and yeah, we have already met that. And also the minimum thrust to weight ratio that will be the requirement is 5:1 ratio, and for us, Hebat 2.0 the ratio will be 8.66:1. Next slide. So this is just some of the parameters from the motor simulation. So for the expected apogee, we'll be having around 10,651 feet. And next is the off-road velocity, which is 99.8, and the maximum velocity of the flight will be 949 feet per second, and the total flight time will be 271. Next slide. So these are some of the requirements from the safety slide review slide. So for the motor casing, we'll be using the 98mm from LOC, and it's a brown craft paper, and it's still on transit, and we'll be expecting it to arrive soon in our hands. Next slide. So the motor casing, we have already have it in our hand, and that's the picture. Next slide.
Okay, can I ask a question about the motor casing?
Sure.
Can you go back to the previous slide that shows it? Okay, do you have the casing now?
Yes, we have it in hand.
Okay, one thing that I want to ask you about is how you're securing the eye bolt at the top into the forward closure.
So actually the forward closure is threaded, and we'll just screw it on the eye bolt.
Okay, and you will have a recovery harness attached then to the eye bolt?
Yes, true.
Okay. you need to come up with a procedure for making sure that the eye bolt can't come unscrewed.
All right, sure.
And there are various ways to do that. Some people will use Loctite. You know what Loctite is?
I'm not sure, but we'll have a look on it. So
Yeah, Loctite is a brand. It's commonly applied to threads so that it makes them it can be a permanent attachment or a temporary attachment depending upon what kind of Loctite that you use. So some teams will do that. My personal preference is to use a cotter pin. And the way that that's done is that you drill a small hole that goes through the stem on the forward closure and then through the eye bolt itself and then out the other side of the forward closure. And then you then you insert a cotter pin. Do you know what a cotter pin is?
nope.
Okay, you can find that online easily, but it's basically a small piece of metal that then goes through the hole in the forward stem, through the eye bolt, and then out the other side. And when you install that, then there's no way that the eye bolt can come unscrewed.
All right, so we'll have that on one.
Right. So a few things you'll need to do something to prevent the eye bolt from unscrewing. If you use the cotter pin technique, a couple things are important. First, don't use a large cotter pin because you're drilling a hole into the threaded stem of the eye bolt, and you don't want to remove too much of the material or you'll weaken the stem. So you just need a small hole, just enough for the cotter pin to go through. And the other thing that's important is to drill the hole as low on the stem as you can, so that that most of the stem going into the top of the forward closure does not have a hole into it. You haven't weakened it, so to speak, by cutting this hole. So let me stop there and just ask Julian and Jimmy for their comments on this, because this is something that's important, and you'll want to make sure that you do a good job in being able to demonstrate that the eye bolt can't come unscrewed from the motor.
Yeah, so typically in the past, and this is true for the smaller rockets, I would use a little bit of Loctite and one of those locking washers. But for this larger rocket, my preference, I would prefer the team to maybe use a swivel in addition to the Loctite combination. That way, they don't really have to drill through anything, and the whole process is just kind of reversible.
Yeah, yeah, the teams will do that. One common thing that teams do is they'll use a locking nut or a nylon nut to secure down to the top of the forward closure, and that technique doesn't really work very well, and you can try your own testing to prove it to yourself, but it's very easy to unscrew the eye bolt if it's, if you were to use something like a split washer or something. It comes loose very easily because it's not really how lock washers and nylon nuts are really intended to be used. So that technique is usually not acceptable. There either needs to be the lock nut or the cotter pin. or I'm
What are your
sorry,
thoughts on,
the Loctite or the cotter pin.
what are your thoughts on teams using a swivel? Has there been any such failure modes?
Well, I mean, I think it's a good idea to use a swivel at the position, you know, close to that eye bolt, because tin cans spin, and it can put a lot of stress on the on this connection point because of that. And so I think having a swivel at that point is a good idea. I don't usually recommend relying on it though, because I can imagine swivels getting jammed or configured in some way so that they don't really do everything that you think they will do. And I would have to say my personal preference would be to use the cotter pin, because there's no way that the eye bolt can unscrew if there's a cotter pin holding that eye bolt in. So I would just recommend looking at it, but it's not the most pleasant thing to build. It's difficult to drill those round surfaces and do a good job at it. So you know, this is just something that you should spend a little bit of time looking into, so that when you get to the site and the question is asked about what you're doing, you'll have a good answer that you've thought through this.
Okay, thank you.
All right, thank you, Jim. I will have all the suggestions in mind and come up with the best possible solution to make sure the eye bolt doesn't unscrew. So can we continue with the next slide? So the next slide is about the rail buttons. We have already purchased the rail buttons from Apogee Rockets. It's a 15-15 dimension given by Astra as well. And just to make sure the rail buttons fit through the launch rail, we'll be bringing our last year's rail buttons as well to make sure it fit perfectly to the rails. Yeah. Next slide. So this is the truss plate that we'll be using to make sure the force exerted is exerted towards the body and not towards the centering ring. And we have this in our rocket as well. And this picture is the semi-assembly of the booster section. So this is the overall setup of the motor assembly. As you can see, there'll be 3 centering rings and 1 at the end, which is the wooden centering ring. And there'll be truss plates and the motor tube. Slide.
May I ask a question?
Sure.
I see a forward centering ring that looks like it's made out of wood or plastic, the brown
Yes.
ring.
The brown ring is made of wood.
Okay, will that be fastened in the body of the rocket itself?
Yes, it will be fastened to the body using epoxy and also to the motor tube.
Okay, good. That satisfies one of my concerns.
Yeah, this is just the rough assembly, and we haven't epoxied the centering rings towards the body yet. So it will be done in a few weeks' time.
Okay, good.
Right.
Mike,
Thank you.
let me go ahead and tell you this concern. A few weeks ago, a team I mentor, University of Florida, had a flight, and they were using a fin design almost identical to yours, with independent fins that are replaceable. They suffered a failure in flight, and it was during the thrust part of the flight that it failed. And there were 2 theories as to how that might have happened. One was fin flutter, but their flutter margin was very good, so we didn't think that likely. The next one was compression, because think about the thrust of the motor and how much weight it has to push forward at acceleration. That creates a lot of stress down here in the motor area. So you need a very strong thing. When you slot your body tube down at the bottom to put the fins through, you've weakened the tube. when you use a through-the-wall fin design, the conventional method, you replace that with epoxy and fin material and it re-strengthens that. But when you simply screw on a bracket to hold your fin, you've lost that strength, or most of it anyway. So I just suggest being very cognizant of the amount of stress that's going to be placed on your body tube there, especially considering how thin your body tube is. Was that too much?
Could you back up one slide, please? Yeah. Okay. So Jimmy, it looks like the thrust ring is pushing on the bottom of the airframe, which is good.
Yeah.
And I think that's it, is for the thrust location.
Well, it looks like it's also going to be pushing on the motor mount tube.
I'm not sure if that's the case.
Well, maybe that's a question here, is will the motor mount tube also impinge upon your thrust ring?
Yes, the motor tube will be attached to the thrust plate as well.
Okay, good. Well, that increases the strength.
All right.
By diverting a lot of the force of the thrust to that upper wooden ring.
Understood.
Okay, I agree.
Okay. Well, my suggestion is to just look at it and think about it. And if you're afraid of this, well, fear is a good reason to test. And that's the best use of fear, is to motivate the testing you need to do. A simple thing to do, what I would do, since I don't have testing equipment, would be simply to estimate the amount of pressure, the force that's going to be placed on the aft end of the frame, and use a static weight equal to that force to stack the thing up and put the weight on it. And if you're scared you're going to break it, bing, do it now. Better to break it now than in flight in New Mexico.
All right, sir. So I think that's all for my part. And if there's no more questions, we can move on to the checklist part.
Yes, I think that's the end of the subsystem assembly. But I think this checklist alone is going to be describing the entire assembly process of the rocket. But I think since it will take much more longer time, we can actually skip it and we can proceed further questions from both of you that is related to the launch checklist, since we have the rocket here in front and we can show it to you directly.
Let me ask you, I missed the one line on one of the slides about you're getting the motor. Can you tell me what arrangements have you made to get possession of the motor?
So for the motor,
I'm sorry.
For the motor, we'll be using the vendor called Off We Go Rocketry.
Okay.
So the vendor will be bringing the motor directly to the spaceport competition, and we'll be assembling the motor before the flight. Yeah.
Okay, so they are going to ship the motor to the site.
The vendor will be on site. He's a mentor for
they're
another
on
team.
site.
Yeah.
Okay. Okay.
All right, sir. Any other questions?
Let me check my list and see if there's anything.
I'm putting something in chat, but it's sort of in addition to the little rant I did about the thrust of the motor. And something I do in my rockets is use multiple thrust rings. I'll spread them out over the length of the motor mount tube and make sure they're all glued well to the inside of the rocket. And that spreads the stress out to a much larger area. They're cheap and easy and they help a lot. So use lots of thrust rings, or I'm sorry, centering rings.
Well, we have covered all of the questions that I had. And I'd just like to make a couple of comments. I think it's really great that you've made your own airframes and your own nose cone and your own parachute. I think that's really an exceptional job. I think most teams are not going to do that, and I commend you for basically making the rocket your own in that way. I think that's just exceptional. And I also think the quality of the information that you've provided is really good as well. What I find particularly good about the information is that although you've provided a lot of information, the very little of it is what I'll call boilerplate or unnecessary information. It's all good, and you've explained the rationale of your suggestions. And what is particularly unusual is that the level of the information is very appropriate. And I really think for a college team, I very rarely see that sort of technical judgment, I guess, in the information that's provided. And so I think I just wanted to let you know that I really appreciate the information that you've provided, and it's very easy with a few questions just to see what you're doing and to review your rocket. I've been looking at spaceport rockets for 5 years, and I've not seen better documentation of a project than what you've done. So I think that I just congratulate you for doing that, and I'm sure that your technical report will be well received. I guess I don't have any other questions. Jimmy, do you have anything you want to?
Yeah, well, first I want to, oh, good, I'm not muted. Concur with Jim about your documentation. It is superb and the best I've seen for any rocketry project here. I don't want to rant about other teams and what they do, but many of the reports are hard to read and hard to understand. Yours is very clear, concise, long, but justifiably long because you're covering a lot of data and doing it very well. So I thank you for that. It helps me a lot. Another thing occurs to, yeah, you apparently can't launch your rocket where you are. This is as much a joke as anything, so please laugh if you think it's suitable. I wonder if it would be possible for you to go to the Bang Thai Festival in Thailand. Are you familiar with that? Well, they launch some ridiculous rockets, but one of my goals is to go to the Bang Thai Festival one of these days, just to watch. But I wonder if they'd let you launch a rocket of this sort there.
Yeah, their safety is a little bit questionable.
Yeah, whether you could transport it there is another big question.
Yeah, it's not that we cannot launch it or we can do that, just that the military regulations and everything is very strict and we have to go through a very strict review and the process is pretty much long. So
Okay.
yeah, and we hope that the next rocket we build, we hope to get a test launch to do it beforehand to bring it to Spaceport America Cup in future.
Yes. Well, with the quality of your work here, I would hope you'd have a good chance of passing their review.
So do you have any questions you'd like to ask us?
Okay, yeah, sir. Regarding the rail button, since we have actually fully fabricated the rocket, and right now, you said that bring the movement, change the placement of both the rail button, right? So I have a suggestion here. Instead of closing the holes of the initial one, we add on another holes at both the airframes that, as per suggested by both of you, which is at this adding one to the centering ring at the booster airframe and another one is at the propeller of the half tube. Will that be okay if we had two rail button holes on it? or we still have to cover the initial rail button hole and make a new one, complete new one? Just to see.
I didn't hear all the questions. You were breaking up a little. Could you ask those questions one more time?
Okay. Hello. Can you hear me now?
Yes.
Yes.
All right. So my question is, initially, both of you suggested to change the location of the rail button on the rocket, right? Which is actually to move it slightly, maybe place it on the centering ring for the booster airframe, and for the aft section, maybe put it on the coupler side, right?
Yes.
Yes,
Okay,
and
so-
let me add to that. That would be another good reason to have multiple centering rings at that point. I'd squish 2 or 3 or 4 of them together to make sure there's plenty of stuff for your rail button to hang on to.
Yes, that is an option. I mean, if you don't want to move the rail button, you could just maybe add a centering ring at the location where the upper rail button is located. And we've seen so many times that a team gets to the rail and loads the rocket and just accidentally pulls the button off. And so we want to make sure that that does not happen, at the last minute as you're getting ready to fly.
All right. Okay. That answered my question, sir. Thank you.
Okay, I'll just add one comment. You do have the option, if you want, to add a third rail button higher on the rocket. It's not an easy thing to do with 15 buttons because their tolerance is not large. But I have rockets where I do that just to make sure that they are, that you minimize the amount of torque on the rail buttons, as the rocket's on the pad. So some teams will do that. They'll add a third rail button higher up on the rocket. Just as a comment.
We will take that into the consideration, and then regarding all of your comments, what we will do, we discuss with our mentor, and then we will provide the result or the latest decision that we have taken via email.
Okay.
Yeah, if that's the case, then that's the end of the presentation today. And thank you so much for spending your time with us. And I apologize for dragging the presentation more than 45 minutes because we wanted to make sure that our safety reviewers understand each aspect of the rocket, so that to make sure that this rocket flies safely in spaceport this year.
Well, we want a successful flight, a safe flight, but we want it to work too. We like to see them work. So yes, thank you very much for your time as well. I think I'm just going to send you a little bit of information on deployment bags. And if you have any questions on those, you can holler back as well. Other than that, good luck. If you have any other questions, just be sure to ask them.
All right. Thank you, sir.
All right. Thank you much.
And thank you all. This has been wonderful. You're a great team.
Yeah.
Proud to be working with you.
Looking forward to
Thanks,
see
Jimmy.
you.
Thanks, Jim.
Yeah. Bye-bye.
Okay.
Thank you, Jim.
Bye-bye.
Thank you.
Thank you.